Hello there. This lecture is going to introduce you to several common ways to describe your data using numerical measures. So in the last lecture, you looked at how to display your data in tables and graphs to summarize it. Now we're going to use numbers to summarize data and understand how values or scores in your data set are related to one another. So here's the brief outline of today's lecture. So I'm going to start off with percentiles, which is something that you were introduced to in the frequency distributions lecture, but we're going to get into some different ways to find percentiles when you don't have access to all the raw data. Then the popular measures of central tendency, so the mean, the median, and the mode. And then when it's appropriate to use each. So we have multiple measures of central tendency. Although we love to use the mean, that's typically the measure that we favor, we have to have the median and the mode because there are certain situations where the mean is just not appropriate to use. Then I'll look at measures of variability. Variability is just a fancy word for differences or spread in scores. And then finally, I'll show you how to use the mean and the standard deviation together to understand how extreme scores are in a data set and to understand how spread out scores are in a data set relative to the mean. Because if you have a really large mean, then you're going to have a larger standard deviation, which this will all make sense soon, regardless of how spread out scores are. Okay, percentiles. So percentiles just help you identify where a specific value is located in numeric order in terms of the whole entire data set. So is it higher than a certain percentage of scores or lower than a certain percentage of scores? You've probably heard of percentiles a lot when it comes to like your scores on an IQ test. So, or ACTs, you could say, I'm at the 80th percentile and everybody's excited about that. But few people actually know exactly what it means. So here's a nice picture of percentiles and where they are located in your distribution along the x-axis down here at the bottom. So this is just an example distribution looking at IQ scores in the population. And the average, or the mean, as you'll soon find out how to calculate, the mean IQ score is 100. It's right smack dab in the middle. And most people have a score around the average or the mean, with a few people being in that extreme high end and a few in the extreme low end. So when you think about percentiles, the percentile tells you the percentage of scores that are less than or equal to a given score. So if we look at these percentiles in the x-axis here, you could say that a score of 50 on an IQ test is in the 10th percentile, meaning that you did equal to or better than 10% of the distribution, or 10% of the scores. Another way to think about it would be, because this represents 100% of the scores, if you did as well or better than 10% of the scores, then 90% of people had a score that was higher than you. So you're not feeling too good. So a lot of times when you're thinking about percentiles, if a higher value is more desirable, then you want to be in a higher percentile. For instance, if you were at the 90th percentile, then only 10% of people who took the IQ test did better than you. And you did as well as or better than 90% of test takers. So that's pretty impressive. You'd want to be at the 90th percentile. Now, if we were measuring number of absences, for example, and you prided yourself on coming to work often and not being tardy or absent a lot, then a higher percentile would not be desirable because that would represent a higher number of absences. So if you were at the 20th percentile for absences, then that means that 80% of employees were absent more than you were, and you were absent as much or more than 20% of the distribution. I had to think about that for a second. So I hope this picture helps you understand where percentiles fall on the distribution. So here's some examples, and I already kind of alluded to some of these. So the percentile just tells you what proportion or percentage of values in the data set are less than or equal to a specific value. So again, if your IQ is at the 95th percentile, then your IQ is as high or higher than 95% of the population. And you could also say only 5% of the population has an IQ score higher. So in this case, again, higher scores are more desirable. You want to be in a higher percentile. If we're looking at late arrivals, you don't want to be in the 95th percentile because that means You're on the extreme high end of absences, or sorry, late arrivals, and that's not a desirable thing. Also, if you look at a performance appraisal score, higher scores are better. So if you were at the 25th percentile, you're not looking too good. So 75% of your coworkers would have had a better performance appraisal score than you, and that's not desirable. So if you were considered at the 90th percentile for weight, would you be considered heavy? Think about that for a minute. If you need some time to think about it more, go ahead and pause and keep thinking about it until you have an answer, and then resume this video to see what I tell you. All right, I'm going to draw a picture to look at this. So if you were at the 90th percentile for weight, would you be considered heavy? So if we drew the distribution of weight like this, roughly, so different weights, and this is our frequency or number of people. And let's go ahead and assume that weight is normally distributed. Most people fall in the middle, and then we've got some who are really heavy and some who are really small. If you were at the 90th percentile, you'd be right around here or higher. And if you think about how we write our scores in our data set, we go from the lightest to the heaviest. So if you were at the 90th percentile, you would be considered heavy. All right. What if you were at the 15th percentile for annual salary? Would you be considered rich? So think about this one for a minute. So if we drew this distribution, again, we'll assume it's pretty much a normal distribution, starting at no money at all to lots and lots of money. If you were at the 15th percentile, you would be right about here, right? 15% would be below, and then 85% would be above. Would you be considered rich? Not really. So now I want to talk about the percentile location index. So this is a useful tool that you can use whenever you want to identify what score is at a specific percentile when you have the raw data without going through and finding the percentile for every score in your data set. So this is a nice shortcut when you don't want to use the procedure that I showed you with the frequency distribution tables to identify the cumulative percents or the percentiles. So I represents the location of the score in numeric order from the low end. So P, when we look at the formula for I, represents the percentile of interest. So if you're looking for what score is at the 90th percentile, P would be 90. Then you divide that by 100 to turn it into a proportion. So it starts off as a percentage, divided by 100 to turn it into a proportion. And then you multiply that value by your sample or population size, depending on what you're working with. So remember, lowercase n is sample size, uppercase N is the population size. Now, if you calculate I and you end up with a whole number or an integer, then you're looking for the score at the position identified by I and the score right above it from the low end. So to find out what is the actual score at that percentile, you take the score at the ith position, and then you add it to that score that's right above it, and then you divide it by 2. So you're essentially finding the average of those two scores, or the mean of those two scores. Now, if you calculate I and you get a decimal, or a non-whole number, or a non-integer, then you just round that value up to the next whole number, and that tells you the position of the score at that specific percentile. So let's do an example. Let's say that the manager at Chase Bank on Green Valley Parkway collected some data on the mean or average time in seconds that all 10 of their tellers had to complete transactions. So if we see this data, each number represents one teller and how long it took them on average to complete 10 random transactions. So let's say that the manager collected this data for the purpose of awarding merit raises to those employees that had low transaction times. So the criteria for this would be in the 20th percentile or lower. So remember, sometimes high scores aren't desirable, right? Or high percentiles aren't desirable. If you have a situation where performance is based on short transaction times, then you want to be in the low end of that distribution. Okay, so let's do this example where we are trying to identify what score is at the 20th percentile so we can figure out which scores in this data set are going to be at the 20th percentile or lower, and then which tellers would receive a raise. Okay, so let's go ahead and figure out I, because our scores are already in numeric order. That's the first step. If the scores aren't in numeric order, make sure you put them in numeric order, because remember, once you find I, you're going to use that to count from the low end. Okay, so the formula for I, remember, is the percentile of interest divided by 100 multiplied by the sample size, or in this case, the population size, because we have these 15 tellers and that's all who work at the bank. Okay, so, and we know we have 15 tellers because you can count, there's 15 scores here. So P is 20, divide that by 100, multiply that by 15. You end up with 0.20 times 15, which gives you a value of 3. Well, 3 is an integer, so we're going to use the third and the fourth score. So we're looking for the third plus the fourth score, and then divide that by 2. So let's go ahead and count first score, second score, third score, and fourth score from the bottom. So we're looking at a score of 87 and 88. So 87 plus 88 divided by 2, and that gives us 87.5. So if we're thinking about who gets a merit raise, who has a score of 87.5 or lower, then the person that had a 66, a 69, and an 87 would get the raise. This person who had an 88 came really close but didn't quite cut it. So only 3 people would get a raise in this situation. Now, what if the manager wanted to use this data to fire people? So let's say if you're in the bottom 20% of transaction times, you deserve a raise. But if you're in the top 70%, we need to get rid of you because you're taking too much time and our lines are too long. So now we're looking for what score is at the 70th percentile or above, so we can fire them, unfortunately. Maybe we can give them training instead. That sounds nicer. Okay, so these scores are already in numeric order. So we're going to start by finding the percentile location index. So remember, that's the percentile divided by 100 multiplied by, in this case, our population size. Now we're looking at the 70th percentile, multiplying that by 15. So this gives us 0.70 times 15, and that gives us a value of 10.5. Well, 10.5 is not an integer, so we'll round that up. We are looking for the 11th score from the low end, right? So let's see. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. The 11th score is a 122. So we would be firing or giving training to the people that had a 122, a 124, a 137, 142, and 156 for their mean transaction time. So 1, 2, 3, 4, 5 people would be in question. So now let's look at measures of central tendency. And the three primary measures of central tendency are the mean, the median, and the mode. So here's a silly cartoon that you'll probably understand once you watch this part of the lecture. So the mean, again, is just a fancy word for the average. And remember population parameters and sample statistics. So a parameter is a number that's used to describe a population. A statistic is a number that's used to describe a sample. So in this case, the population mean would be a parameter, the sample mean would be a statistic, and there's different notation depending on whether or not you're using a population or a sample. So if you're looking at a population, then you use this little mu symbol to symbolize the mean, and it's equal to the sum of all the scores in the data set. So you literally just add all the scores together, and then you divide it by the total number of scores in your data set. Now that's the same thing that's going on in the sample mean. You add all the scores together, divide that by the total number of scores in the data set, but the symbol is a little bit different. This is X bar represents the sample mean. So this nice little sigma sign just represents summation, addition, adding all the values of X. X is usually just the notation for a score. Okay, now there's something that's called sampling error. And that concept is the difference between a parameter and a statistic that's due to chance or just systematic error. So no matter what, in most cases, if you take a sample from the population and you look at their mean compared to the population mean, there's going to be some differences, and we call that sampling error. So let's look at an example where we want to find the mean transaction time for two different tellers. So this is going to show you how that data in the previous example was generated. Remember, there was 15 numbers there. Each number represented one teller. Now I'm going to show you how you would find the mean transaction time for these two tellers that were represented in that previous data set. So we've got Maria and Bob, and just looking at their data, I can see that they have some high scores, some somewhat low scores, but it's kind of hard to tell overall who has the longer transaction times. So we need to figure out what the mean is for each. So the best way to do this, to find your sum of X, just add all the scores together. There's 10 scores in total. So for Maria, you add her scores together, you get 990. Divided by 10 scores, 99 is her mean. For Bob, add his scores together, you get 870. Divide it by 10 scores, and you get 87 for the mean. So overall, Maria had a higher or a longer transaction time. So now let's move on to the weighted mean. So the weighted mean allows you to account for relative influence of a particular value based on the weight assigned to it or the number of occurrences or the frequency associated with it. And the weighted mean is used when you don't have access to the raw data, but you're either using a frequency distribution table or you have a situation where different scores are given different weights. A good example of different scores being given different weights are sometimes in classes. So they'll say, okay, we're going to use a weighted scheme for our class, for our grades. So 70% of your grade comes from exams and 30% of your grade comes from homework, that sort of thing. So if data is presented in the frequency distribution table, again, you would use this process to figure out the mean as well. And I'll just break down this formula for you. So weighted mean, you see either the mu with a little w subscript, meaning the weighted mean for a population, or x bar with a little w subscript, meaning the weighted mean for the sample. And then the numerator of this is saying the sum of the weight for a specific value. So I is still representing, a specific location of a score. So the weight or the frequency of a specific value multiplied by the value, or the frequency multiplied by the score that has that frequency. You can think about it that way. And you do that for each score in your data set, and then you add it together. So if you think about order of operations, remember PEMDAS, please excuse my dear Aunt Sally. So you start with parentheses, then you move on to exponent, then you do multiplication, then division, then addition, then subtraction. Well, in this case, we have multiplication and addition, so you do the multiplication first and then you add at the end. Then here, you just take the sum of the weights or the sum of the frequencies, and that's essentially your sample size or your population size if you're working with a frequency distribution table. So here's an example where we're looking at a Nike plant, and we have 4 or 5 different plants. And the average medical payment per employee is listed here. So in plant 1, the average medical payment per employee was $7,400. In plant 2, it was almost double that. So I'm thinking something's going on at plant 2. They're having a way higher average medical payment per employee. But then you also look at the number of employees, because we can't say, okay, what's the average, medical payment per employee across all of the Nike plants? You can't just add these means together. You can't even add these means together and divide by how many means there are, because you have to take into account how many employees were at each one of these factories. So here's this example all spelled out for you with the calculations. So to find the denominator of your weighted mean, the sum of W, or the total frequency, you add those frequencies together. So the number of employees was what we'd be looking at here. So how many employees were there in total across those 5 Nike plants? You add 123 plus 402 plus 256 plus 109 plus 67. You end up with 957 total employees. Then, so that's our denominator. Then you need to figure out the sum of all of the medical payments together. So that's this numerator of your weighted mean formula. So to find the total amount that Nike paid for medical across all 5 of these plants, you need to take the average medical payment per employee and then multiply it by the number of employees. That'll give you, so plant 1 spent a total of $910,200 on medical payments. Plant 2, so what was the average multiplied by how many employees? They spent $5,788,800 on medical across all their employees. So I hope that makes sense where that data is coming from and why you need to take the frequencies of each X value into account when you're trying to figure out the total sum of all the values in your data set. So if we add all those together, we take each value, multiply it by its weight or its frequency, then add all the way down, you end up with 10,731,300. So that's the numerator of your weighted mean formula. So then you take that total, so all of the money spent, divide it by how many employees, and you end up with the mean medical payment per employee for the 5 Nike plants. So that is $11,213.48. Now, if you compare that to the average medical payment per employee separated by plant, it looks rather high. But the reason that it's higher than most is because this really large mean of $14,400 came from the bulk of the employees in the data set. So the weighted mean gives the values from a higher frequency more weight in the final calculation, so that it's a more accurate representation of the entire data set of all the things you're interested in. So here's an example where we are looking at the number of no-shows for flights in a specific day. And we'll go ahead and call this day a population. Say we're only interested in this day. And if we look at this frequency distribution table, you can see that 37 flights had no-shows, so 0 people didn't arrive. 31 flights had 1 no-show, 20 flights had 2 no-shows, 16 flights had 3 no-shows, 12 flights had 4 no-shows, and 4 flights had 5 no-shows. Now, if you think about the mean formula, the sum of x divided by n, you can't just simply say, oh, well, number of no-shows, so that's like our x, and we can just add 0 plus 1 plus 2 plus 3 plus 4 plus 5 to get our sum of x. You cannot do that. That's not going to take into account the number of flights with each one of those no-shows. You have to take the frequency of each value into account. Because think about it, if we wrote this data out in raw form, we would write 0 37 times, 1 31 times, 2 20 times, 3 16 times, 4 12 times, and 5 4 times, then we can add all those together and get the sum of x. But it's much simpler to just multiply each value by its respective frequency, add down, and that gives you the sum of x. So the way, again, that that's symbolized is with that weighted mean formula, where we're looking at, now I'm going to symbolize it using x bar because we are working with, well, no, I said we're working with the populations. Let me make that. All right. So we'll do the little mu bar, or mu with the W. So that is equal to the sum of each weight or frequency multiplied by its respective score or value in our data set, divided by the sum of all the weights or all the frequencies added together. Okay, so I'm going to go ahead and start by finding my denominator. And to find my denominator, I need to add up the total number of flights. So this is like my F or my W, my frequencies, my weights. So 37 plus 31 plus 20 plus 16 plus 12 plus 4 gives me a sum of W that is 120. So on this day, there were a total of 120 flights. Well, now we need to figure out the total number of no-shows for the day. So to find that, we need to create this new column of WI, XI. Remember, order of operations, we first need to multiply before we can add. So we have to multiply each one of these together. So we have, I'm just going to go ahead and write it right here. 0 times 37 is 0. 1 times 31 is 31. 2 times 20 is 40. 3 times 16 is 48. 4 times 12 is 48. And then 5 times 4 is 20. You add those together, and you get the sum of each weight or frequency multiplied by its respective score, and you end up with 187. So how many no-shows were there in total today? 187. Divided by how many flights? 120. So 187 total no-shows divided by 120 flights, and you end up with a weighted mean of 1.558. So on average, there was 1.558 no-shows per flight. So here's an example where you have weights, not frequencies, that are assigned to different values in your data set. So let's say that employees who are looking for a job in HR management have to complete a battery of selection tests. But each selection test, while important, some are a better predictor of performance than others. So you assign a larger weight to those tests that tend to be a better predictor of performance. So this job appears to really focus on employment law, followed by the ability to do a job analysis, followed by the ability to do a performance appraisal, and then math skills, although important, appear to be the less heavily weighted piece of your selection tests. So you can see these weights. The higher the weight, the more value assigned to that type of selection test that measures these specific abilities. Now, if you think about weights, when you add your weights together, because remember, this is going to encompass 100% of their final score, you'll end up with 1. So if you turn these into percentages, like 20%, 40%, 25%, and 15%, then 100% would be encapsulated in all those weights added together. So when you think about that formula that we looked at before, this value in the denominator is going to be 1. So I'm just going to ignore it because any number divided by 1 is equal to itself. So let's go ahead and figure out if John got these scores on these 4 selection tests, would he end up with a final score of 80% or above based on how heavily weighted each of these are. Now I'm looking at this and I can see that on the one that counts for the most of your final score, the employment law test, he aced it. And then he didn't do so hot on the rest of it. So let's see if acing that employment law test will put him into a high enough score to make up for these that he didn't do so well on, that didn't count for so much of his final score. So if you look at this, just like we did before, you take each weight, multiply it by its respective score. And so you take 0.20 times 70, 0.40 times 100, 0.25 times 70, and 0.15 times 60. Add those values together, and you can see that he ended up just above a passing score. Again, didn't do so well on those other tests, but he did do amazingly well on the test that makes up for the majority of the points if you compare them to how much weight is given to the other tests. Now let's look at the median. So the median is just a midpoint. It identifies the middle of your distribution, and it separates the top 50% of scores from the bottom 50% of scores. Now there's different statistical notation depending on if you're working with a sample or a population. If you're working with a population, then the median is this U with this funky little tilde above it. And the sample mean is symbolized as an M with a D subscript. Now just like the percentile location index, where you're trying to find the location of a score, the median, you're also looking for the location of a score. So the median index functions quite similarly to the percentile location index, only there's a little bit of a different formula, but we're still going to be finding I and then counting to find the position of I in our data set and what score is at that position. So I is equal to N divided by 2, your sample size divided by 2. Or if you're working with a population, you could say that N is equal, or I is equal to uppercase N divided by 2. So remember, just like with the percentile location index, if you calculate I and you get a non-integer or a decimal, which happens when you have an odd number of scores, then you just have one midpoint. You take I, you round it up, that's the location of your median. If you get an I that is a whole number, then you want to look at the score at that location and the score just above it, and then divide those two scores by 2. Now, unlike the percentile location index, once you find I, you still have to put your values in numeric order, but you can start at the high end or the low end, and you're going to end up in the same spot. Because remember, the median is the midpoint. So you're going to find the midpoint from the high end or the low end. It doesn't matter. You're going to end up in the same place. So here's the mean transaction time among tellers at Chase Bank, so those 15 tellers that we were looking at before. And if you want to know what the median is for these transaction times, the first thing you need to do is you need to find I. Well, there's 15 scores. We know there's an odd number of tellers, so there's going to be one midpoint. So when we find I, we take that sample size or population size of 15. Let's change this to an uppercase N. Divide that by 2, you get 7.5. Round 7.5 up to 8. We're looking for the 8th score. So you just say, okay, well, here's the lowest score. So 1, 2, 3, 4, 5, 6, 7th, 8th score. Or we can go from the high end and do the same thing. So the first, second, third, fourth, 5th, 6th, 7th, 8th score is still 104. Now let's say that Maria quit. So her mean score, remember that we calculated earlier, her 99 is no longer in our data set. So now we're left with an even number of tellers. We have 14 tellers. I'll change this to an N. So now we're going to have two midpoints. So when we calculate I, we have 14 tellers. 14 divided by 2 is 7. So we're looking at the 7th and the 8th score. Now, no matter which way you go about it, you're going to find the same two scores. If you start at the bottom and work your way up, count to 7th and 8th. Or you can start at the top and work your way down, and you're going to end up with 107 as your 7th and 104 as your 8th score. You add those two scores together, you get 211 divided by 2, you get 105.5. That is your new median after Maria quit. Now let's do a handwritten example. So let's say that both Maria and Bob quit. So now we are left with 13 tellers. So N equals 13. So we have an odd number of tellers. We're going to have one midpoint, one score that's our median. We don't have to find the mean of two scores to identify our median. So if we say, okay, I is equal to N divided by 2, well, 13 divided by 2 gives me 6.5. So I need to round that up to the 7th score in my data set. So what's the 7th score? Let's see. 1, 2, 3, 4, 5, 6, 7th score. I can start from the other end. 1, 2, 3, 4, 5, 6. Hey, that's still my 7th score. So my median is 107. Let's do another example. So let's say that Maria, Bob, and Christine quit. And Christine mean was a 124. So that disappeared from our data set. Well, now we have a situation where we have an even number of tellers at Chase Bank. So we're going to technically have two midpoints that we have to find the mean of to identify what the median is. So I is still equal to N divided by 2, and 12 divided by 2 is 6. So we're looking for the 6th score, and then the one just above it. So the 7th score, divide that by 2. Remember, this doesn't mean that 6 plus 7 divided by 2. It's the 6th score plus the 7th score divided by 2. So let's find the 6th and the 7th score. So 1, 2, 3, 4, 5, 6th and 7th score. If you go the other way, 1, 2, 3, 4, 5, 104 and 107 are the two scores that we want. So 104 plus 107 divided by 2. We end up with 211 divided by 2. And our median is 105.5. Think about it. So 105.5 would be like right here. There's 1, 2, 3, 4, 5, 6 scores above it. 1, 2, 3, 4, 5, 6 scores below it. It's our median. So you can also use the median use the median index to find the median within a frequency distribution table. So let's go ahead and figure this out. So first thing we need to know what our N is, because I is equal to N divided by 2. So you add up the total number of flights. So 37 plus 31 plus 20 plus 16 plus 12 plus 4. And we can see that we had 120 total flights. So that is our population size. So 120 divided by 2 gives us an integer, 60. We have an even number of scores, so we have two midpoints. The first midpoint is the 60th score. The second midpoint is the 61st score. And then we're going to divide those two scores by 2. So we can use the frequency distribution table to identify what score is at what position. And we focus on the frequency column at first. So the number of flights, or the weight column, depending on how you want to look at it. So I usually start, it doesn't matter what end you start on, but I usually start at the end that has the highest frequency because I can do less counting. But so let's start at the top. So scores 1 through 37 are 0. Scores 36 through 38, So 37, add that to the 31. So scores 38 through 68 score are equal to 1. And guess what? 60 and 61 fall in between that. So we know that both of our scores that we're looking at are a 1. So this becomes 1 plus 1 divided by 2 is 1. That is our median. Now you could start at the bottom and work your way up if you like. So scores 1 through 4 are 5. Scores 5 through 16 are 4. Scores 17 through 33 are 3. Score 34 through 54 are 2. And then score 55 through 86 is 1. And 55 through 86, 60 and 61 fall between that. So you're still looking at 2 scores of 1 as your 2 midpoints. Now the mode is pretty straightforward and simple. The mode is just the most frequently occurring score in your data set. So you can simply look in, if you have it in your frequency distribution table, look at your frequencies and figure out which number is the highest. It's pretty clearly 37 is the most highest frequency. And what score occurs 37 times? 0. So 0 is our mode. Now you can also put your data into a frequency distribution graph. And that'll also tell you pretty quickly what the mode is. It's the tallest bar in a histogram or bar graph, the highest point in your distribution here. That identifies your mode of 0. Now, I'll talk a little bit more about shape here in a minute, but you can have multiple modes in a distribution. So let's say that 1 also occurred 37 times. Then our mode would be 0 and 1. And sometimes people will identify multiple modes if there are 2 scores that do occur more frequently than most other scores, but not the exact frequency. So you could maybe make the case, let's go ahead and call 1 a mode as well, because 1 and 0 occur quite more frequently than 2, 3, 4, and 5. So now let's talk about how you select the most appropriate measure of central tendency. Now, the first thing I want to point out is that we will talk about variability in a little bit, and the mean is your reference point for variability. So no matter what your shape of your distribution is or your scale of measurement, even though typically we don't use variability unless we have an interval or ratio scale, but regardless of scale or shape, we're going to be using the mean if we're talking about our score's variability. Again, the mean is the reference point for variability. But on a purely descriptive level, if you're just wanting to summarize your data really quickly and report it with a numeric measure, you need to consider your scale of measurement and the shape of your distribution before you select your measure of central tendency. So we always prefer the mean, but sometimes the mean is not appropriate. Now, sometimes there's a specific question that's at hand that it makes more sense to use a specific measure of central tendency, regardless of what you're measuring. So, for instance, if you are really interested in understanding your target demographic, well, that's probably going to be a mode that you're looking at. You want to look at, like, for instance, if you're looking at, what age group most frequently buys my product, most frequent, that's the mode, you would be looking at the mode. Now, once we look at shapes of distributions, you'll understand why this cartoon is funny. So let's first discuss when you can use the mean. So again, the mean is the first choice because it is that reference point for measures of variability. So variability is spread. We talk about spread of scores from the mean. And it is always used in inferential statistics, but we are not going to go there in this class. The mean is only appropriate when you have continuous data that's on an interval or ratio scale. So remember, continuous data, you can have any incremental values in between whole numbers. And then interval or ratio scale, not only do you know the direction of differences, but you know the magnitude. So you not only know that a score is higher, but you know how much higher it is than the other score. And you must be able to calculate the sum of x. So you can't use the mean when you have an open-ended distribution. So for example, if I asked you how many semesters you've been at NSC on a scale of 1 to 5. So 1 would be 1, 2 would be 2, 3 would be 3 semesters, 4 would be 4 semesters, and then 5 would be 5 plus. That's an open-ended distribution. We don't have access to all of our data because who knows what 5 plus entails. So you can't calculate the sum of x to get the mean. Or when you have a group frequency distribution, you lump scores into groups. You don't have access to the raw data. You cannot calculate the sum of x to then calculate the mean. Also, you can use the mean when you have a situation where you have normal or rectangular distribution. But if you have a skewed distribution, you do not want to use the mean because the outliers in your data set can pull the mean towards it, and then the mean is no longer a great representation of your data. And that's the whole point of measures of central tendency. You're trying to find a number that accurately describes the overarching trend in your data. So you can use the median when you have data on an ordinal scale. So remember, ordinal data, you know the direction of differences, but not the magnitude. So like first, second, third place. You know the person who finished third finished after the person who finished second, but you don't know the difference. Or when you have a grouped frequency distribution, you can go ahead and use the median because you don't have to calculate the sum of x, but you still have values that are in a meaningful order, so you can identify a midpoint. Or when you have data that's on an interval or ratio scale, but it is skewed. So one way to think about this process of elimination when you're determining your measures of central tendency, you first consider the scale of measurement. If it's ordinal, you use the median. If it's nominal, you automatically use the mode. If your data is interval or ratio, then you have to consider the shape of the distribution. If the shape is skewed, you use the median. If it's not, then you use the mean. So here's when to use the mode. Whenever you have nominal data, you use the mode. Remember, nominal data is purely categorical. It has no numeric value whatsoever. It's just labels for different groups. So you can't put them into any kind of meaningful numeric order. So you can't identify a midpoint, and you can't calculate the sum of x. So you use the mode. Also, sometimes it makes more sense to use the mode when you have discrete data because the mode is never a decimal, whereas the median and the mean can be decimals. And if you have discrete data, remember it's fixed to whole numbers. So for instance, when you see the census data reports and they say the average number of children or the mean number of children is 1.875. Well, that's a little off-putting because you can't have a fraction of a child. So you may want to say, you know, what is the mode number of children? But you may opt for the mean anyway. It's just kind of bothersome when you have a discrete variable that's described with a fractional number or a decimal. You can use the mode when you have open-ended distributions as well. You can't use the median because what if your midpoint falls somewhere in that open-ended piece? So that 5 plus, for example. Well, you're not going to know what that score is. So then, when you have data on an interval or ratio scale that has a bimodal non-normal distribution, you can use the mode. And I'll show you some pictures of shapes and why, in that case, when you have a bimodal non-normal distribution, the mode is a much more accurate representation of your data. So let's say we were looking at a frequency distribution graph representing the number of semesters at NSC among a sample of students. So about 27 students had been here for 1 semester. About 4-ish students have been here for 2, so on and so forth. We have a situation where this is what's called a positively skewed distribution. We've got just a couple in the high end, but the vast majority haven't been at NSC for very long. And if you calculate the mean for this data, you get 2.471. That's not a very accurate representation of our data. But the mean and the mode, or the median and the mode are. The median and the mode equal 1. That is a pretty accurate representation of the fact that most students in the data set had only been here for 1 semester. So the problem with skewed distributions is that these outliers, these not so frequent values in your data set, pull the mean towards it because the mean uses every single value in the data set for the calculation. So here we have a situation where we have ratio data, it's skewed, you'd want to use the median. So I just want to show you an example of how sometimes the mean is not a very good representation of the data. So in general, here I'm going to show you some shapes of distributions where the mean, median, and mode would be located in the distribution, and then the underline represents which measure of central tendency is most appropriate. So here let's look at a distribution of weight. So in this sample, most people were around, between 180 and 220 pounds. We had some people who were really heavy and some people who were really light. So this is a situation where we have ratio data, and it's a normally distributed distribution. So we would want to use the mean in this case. But one thing I want to point out, when you have a normal distribution, your mean, median, and your mode are equal. If you have a roughly normal distribution, then your mean, median, and your mode are pretty close in value. So sometimes you can look at your three values and try to identify the shape of your distribution without actually drawing it out. Here's a rectangular shape. So let's say that I had 4 children and I looked at their IQ test score. One had a score of 100, one had a score of 101, one had a score of 102, and one had a score of 103. So there's no mode in this case because the frequency is 1 for each value. And your mean and your median would be roughly the same value in this case. And you would go ahead and use the mean to describe your data. Here's a negatively skewed distribution where the bulk of scores are in the high end, and then we have a few that are in the low end. Well, in this situation, looking at final grades in Econ 261, believe it or not, my distribution has looked like this in the past. Most people do pretty well. So your mode is going to be the largest value. Your median, of course, is in the middle. And then your mean is going to be the lowest value when you have a negatively skewed data set, because these low values are dragging the mean towards it and away from the true trend in the data. So the median you'll always find is between the mean and the mode, even if it's skewed. And in this case, you would want to use the median. We have a skewed distribution with ratio data. Here's another skewed distribution with ratio data, but now it's a positively skewed distribution. So if you look at the number of crashes this year in millions and the age of the driver, this distribution makes it look like those young people do not know how to drive, right? They're just having tons and tons of accidents. And in this case, again, we have skewed distribution with ratio data. You would want to use the median. So you could say, the median age of drivers who have crashes is 27 or 28. Okay, now think about how you can measure and present data and how things can be misleading. So this is looking at kind of the same thing, right? We're still looking at age of driver and accidents. And before, it looked like those young people did not know how to drive. But once you control for the number of miles driven, your distribution changes quite dramatically. And this is actually based on real data. So think about it. Elderly people tend to drive far less than younger people. So here, it looks like they're really safe drivers. But in fact, it just means that they aren't driving as much as the young people. So once you control for how much they're driving, you can see that the older and the younger folks tend to get into accidents more often than people who are middle-aged. Now think about it. If you have this bimodal distribution and you said, oh, the mean age of driver who's having an accident once you control for miles driven is 48. That is not an accurate representation of those data at all. It doesn't represent the fact that the younger and the elderly are more reckless than the middle-aged people. So here we'd want to use those modes to describe our data. So now let's switch gears and look at variability. Remember, variability is just a fancy word for the spread or the differences of scores in your data set. So how consistent are scores? Now there's several measures of variability. I'm only going to focus on the standard deviation. Another common measure of variability is the range, where you just take the maximum value in your data set and subtract the minimum value. Or like for instance, if your maximum score was a 109 and your minimum was an 89, you would say 109 minus 89, okay, my range is 20. Or you could present your range as 89 to 109. That's pretty straightforward and simple. I'm going to focus on standard deviation, which is a little more complex. Okay, so the standard deviation just tells you the typical spread of scores relative to the mean of all the scores in your data set. So there's two different calculations for the standard deviation, one for the population, one for the sample. So for the population, you can see this is called sigma, this little funky like O. That's the symbol for population standard deviation. S is the symbol for sample standard deviation. And let's go ahead and break down these formulas. So this little SS in the numerator, that's called the sum of squared deviations, and that's consistent across both formulas. Now there's two different ways to calculate the sum of squares, or the sum of square deviations. The first one is the definitional formula, this guy right here. I never use that in practice because it leads to a lot of errors, but I leave it there for a reason. I want to explain how it helps you understand what the sum of square deviations is measuring. So you could find this value by finding the mean of all values in the data set, then taking each score in your data set, subtracting that mean, so you're looking at the difference between each score and the mean, which is at the heart of the standard deviation, and then you square those values, and then you add them together. Now the reason that you have to square is if you took every single x value minus its mean and added those together, you'd get 0 every single time. So you have to square each one of those values to get rid of negatives, then you add them together, and you end up with the sum of squares. So thinking about the definitional formula, we're looking at squared differences, right? We had to square them so they wouldn't equal 0, sum of squared deviations. So that's why when you look at the population and the sample standard deviation formula, you see this square root here. We're essentially undoing the fact that we had to square the deviations to avoid negatives. Now, magically, there's this computational formula that although it looks more complicated, it's not, and it gives you less chance for error. I find it much easier to use, and it gives you the same value that you would get if you used the definitional formula. But I'm going to cross this out. I do not want you to use that. I'm only going to focus on the computational formula. So that gives you information on the numerator of these values. Let's turn our attention now to the denominator. So for the population standard deviation, you just divide by the number of scores. But for the sample standard deviation, you divide by the number of scores minus 1. Now, to keep it simple, the reason that we do that is because typically samples, remember samples are a subset of your population, samples don't usually capture the extreme scores from your population or the outliers. So samples tend to underestimate how spread out your scores actually are in the population. And remember, the whole reason that we care about samples is because we're wanting them to tell us something about the population. And if samples tend to underestimate the true spread of scores in the population, we can make a nice little correction to our calculation for the sample standard deviation to try to minimize that sampling error. So whenever you think about fractions, if you have a smaller number in the denominator, the overall value tends to be larger. So by making the denominator slightly smaller, we bump the overall value of the standard deviation up just a bit to account for the fact that we know samples tend to underestimate the variability in the population. Now, if you have a situation where you're using a frequency distribution table instead of raw data, you can think about your formulas a little bit differently. So we've still got our sigma and our s representing population standard deviation and the sample standard deviation. Only here, and the sum of squares is going to look the same, but the formula for sum of squares is different. So for this formula, let me go ahead. Oh, look at this. Remember order of operations. Exponent comes before summation. So here, you're squaring each value and then adding the squared values together. Whereas here, remember, you have to take the frequencies or the weight into account when you're using the frequency distribution table. So you square each x value, then you multiply it by its respective frequency, then you add those together. Just like when you found sum of x for the mean, you had to take into account how many times those values appeared in your data set. Now, if we look at this second value here, this is saying you find the sum of x and then you square it. You add all your x values together and then you square that value. Let me fix this a little bit. The formatting got kind of weird. Well, here, remember, finding the sum of x, what is the total of all scores? If you add all the scores together, you have to take the frequencies into account or the weight into account. So you take each weight or frequency, multiply it by its score, then add that together to get the total if you added all the scores in your data set together, and then you square that. Parentheses comes before exponent, so you solve what's in parentheses first. Then here, the sum of W, that's akin to the sample or population size. So adding up the weights or the frequencies. So that's sum of squares. Then when you look at the denominator here, you've got the sum of W in the denominator for the population standard deviation, which is the same as saying the sample or population, or the population size. Here, you've got the sum of W, or in this case, the sample size, minus 1. Sample size minus 1. Just different notation because you'll be looking at different things in the columns of your frequency distribution table than when you're looking at raw data. So before we move on to some calculations, I just want to give you a little bit of conceptual background about the standard deviation. So remember, the standard deviation tells you the typical spread of scores from the mean. So as the standard deviation increases, that means that you have more spread of scores. As the standard deviation decreases, or if you have a smaller standard deviation, that means your scores are more similar. They're more consistent. They're not as spread out. Well, if you remember your standard deviation, the typical distance, if you have a value in your data set that's 2 or more standard deviations away from the mean, we're going to call that extreme. Because in terms of the typical spread of scores from the mean, your score is 2 times or more spread out, or has 2 times or more of the distance from the mean than most scores. If your x value is 3 or more standard deviations away from the mean, then we'll call that an outlier and say that it is very, very uncommon. It may be some sort of mistake. We have to consider it when we look at our data, that something's funny going on there. So in a little bit, I'll show you how z-scores can help you identify extreme scores and outliers, and this little cartoon will be very funny to you, I hope. Okay, so here's an example where we need to find the standard deviation for these no-show flights for today. So you've seen this table before. Now I'll show you how to use this information to find the standard deviation. So let me break this down so it's not so intimidating. All right. Let me fix this real quick. You should fix this too on your slides. Okay. So first thing you need to find is your sum of squares, because you need to plug that into your formula to find the population standard deviation. So to find the sum of squares, you need to first figure out if we square each score in our data set and add it together, what would we get? But remember, we're working with a frequency distribution table, so you have to square each score, multiply it by its frequency, then add it together to figure out if you squared each score and added it together, what would you get? So to do that, and I'll do some drawing here. So to find this value, we have to take each x value and square it. So that's right here. So each value that's represented in our data set and square it. So 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 2, so on and so forth. Or 2 times 2 is 4, sorry, all the way down. But then, if you added these together, it would give you no good information. Just like adding these together doesn't give you any good information because it doesn't take the frequencies into account. So then you need to take those squared scores and multiply it by how many times those scores appear in your data set. So you've got 0 times 37, 1 times 31, 4 times 20, 9 times 16, 16 times 12, 25 times 4. Now you have those scores that you can add together, and that tells you if you squared each score in your data set and added it together, you would have 547. Okay, let's move on to the next value. So this is saying right here, we need to figure out what is the total number of no-shows, the sum of all the scores in the data set, then we square it. Because this is in parentheses, we do it first. So you need to take your frequencies into account. Remember, you can't just add these together. This gives you nothing. So 0 times 37 is 0. 1 times 31 is 31. 2 times 20 is 40. 3 times 16 is 48. 4 times 12 is 48. 5 times 4 is 20. Add those together. There's 187 total number of no-shows, and you see that here. So as you go through and you calculate these things out, I usually go through the process of order operations. I do one thing at a time. So I'm looking at this. I have some subtraction, some division, and an exponent. I need to solve for my exponent first. It comes first in order of operations. So 187 times 2, that's 34,969. That is the only thing that changes in this next step. I keep my 547 and I keep my dividing by 120. I'm only doing one step at a time. Well, now I'm left with subtraction and division. Division comes first, so I just copy over my 547, then subtract. So 34,969 divided by 120 gives me 291.408. Now I'm finally ready to subtract. So I solve for this, and I end up with the sum of squares of 255.592. Remember, always round to the thousands place. So now I have this value, and I'm ready to plug it into my formula for the standard deviation. So remember, here's my formula for standard deviation. It's the sum of squares divided by the sum of the weights, or the total frequency, how many values are in my data set. So plug in my sum of squares, plug in my sum of weights. So I'm going to solve for my square root last. First, I need to do division. So 255.592 divided by 120 gives me 2.130. Take the square root of that, and my standard deviation is 1.495. Now remember, when we're trying to explain what does this tell us, right? So it's not enough to just say the standard deviation is 1.459 and be done with it. You need to be able to explain what that number tells us about our data. And remember, the mean is the reference point for measures of variability. So whenever I find variability measures, or the standard deviation, I usually find the mean to then make sense of it. So to find the mean, you need to take each weight multiplied by its respective value. So how many times does each score occur? 187, total number of no-shows. And then how many values are in our data set? How many flights are we looking at? 120. Then we get our mean of 1.558. So thinking about the mean and the standard deviation, on average, you would expect there to be 1.558 plus or minus 1.459 no-shows on any given flight on this day. Or, if you want to figure it out, you can take the mean, subtract the standard deviation, then take the mean and add the standard deviation, and that gives you the range that you would expect. So 1.558 minus the standard deviation of 1.459 gives you 0.099. 1.558 add 1.459, 3.017. And since this is a discrete variable, I'm going to turn these into whole numbers. Roughly 0 to 3 no-shows is what would be expected for any given flight on this day. So this is useful because it's not just based on the mean, but it's also based on how consistent are the number of no-shows for each flight. You take that into account, that gives you a nicer picture of your data and what you would expect to find, not only based on what's in the middle of your distribution or what is the mean of your distribution, but also how consistently are scores close to the mean in your distribution. So now let's do an example where we're looking at the standard deviation for transaction times for Miss Maria, going back to Chase Bank at Green Valley. So if we look at this data, this is in raw data form. So we will be using these formulas here. We're looking at raw data now. Even though it's presented in a table, each value is represented on its own. You don't see any F's or weights here. So to find the standard deviation for her, again, we have to start with finding the sum of squares. And the formula is much easier to understand when you're just using raw data. So we have to take each x value and square it and then add it together. So you'll see that here. Each x squared, so this is 109 squared, this is 99 squared, 98 squared, all the way down. Add those together, and that's where this 98,280 come from. Then this one, you've got sum of x in parentheses, so you need to find that first. So you just simply add all the x values together. You get 990. and then you're going to need to square that at some point. And then how many scores do you have in your data set, or in? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 scores. So 10 goes down here. So now we need to do one step at a time, solving for each operation sequentially. So the first thing I want to solve for is my exponent. So everything stays the same. The only thing that changes is that 990 squared becomes 980,100. Now I need to solve for my division. So I need to take 980,100 divided by 10, and that gives me 98,010. Then I just do my subtraction. So 98,280 minus 98,010 gives me a sum of squared deviations of 270. Now I can plug that in to my sample standard deviation formula. Be careful. Make sure you recognize whether or not you're looking at a sample or population, because your formula is different. So plug in my sum of squares of 270. Then divide that by n minus 1, so 10 scores minus 1. I'm left with 270 divided by 9, square root of that. 270 divided by 9 is 30, square root of 30, 5.477. That is my standard deviation. So, on average, Maria's transaction time varies by about 5.477 seconds. So she's pretty darn consistent. Not a whole lot of variation in her transaction times. Now let's figure out Bob's transaction times. So we're looking at good old Bob here. And let's go ahead and write down our formulas so we can work through this. So I know that I'm looking at a sample, so I'm going to write down my sample standard deviation formula, which is the square root of the sum of squares divided by n minus 1. And then my sum of squares formula to find that numerator. So sum of x squared, so squaring all the scores, adding them together, minus sum of x quantity, or in parentheses, so add all the x's together, then square that final value, divided by the sample size. Okay, so let's go ahead and find our sum of x. You just add all these together. So when you add all those together, you end up with 870. Now I need to square each score and add them together. So I'm just going to abbreviate this x squared, because these are our x values. So 125 squared is 15,625. 90 squared is 8,100. 40 squared is 1,600. 100 squared is 10,000. 95 squared is 9,025. 115 squared is 13,225. 87 squared is 7,569. 30 squared is 900. And 108 squared $106.64. Oh, I missed one here. Hold on. I forgot one of his transaction times. So let's add 80 to that. All right, then you sum those together and you get 870. And 80 times 80 is 6,400. Add those together. Sum of x squared is 84,108. So now we have the values that we need to plug in to our sum of squares formula. So sum of x squared is replaced with 84,108. Sum of x is replaced with 870, and we're going to need to square that at some point. N is replaced with, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 transaction times. So 10. Let's solve for our exponent first. So this becomes 84,108 108 minus, so 870 squared gives you 756,900. So 756,900 divided by 10. That's our sample size. So then this becomes 84,108 minus 756,900 divided by 10, which is 75,690. And you end up with 8,418. And that is our sum of squares. Always keep track of your calculations so that you can identify the numbers that you need to plug in to other calculations. So now I can plug in my sum of squares. So I have 8,418 divided by 10 minus 1. So this becomes 8,418 divided by 9. Well, 8,418 divided by 9 gives you 935.333. And 935.333, take the square root of that, you get 30.583. That is your standard deviation for Bob. Bob is not consistent. If you compare Bob and Maria's standard deviations, Bob's standard deviation is 5.6 times higher than Maria's. So Maria has far more consistent transaction time. Her mean is higher. Her overall time is higher, if you remember. But she would be easier to predict than Bob, who has very inconsistent transaction times. He's just all over the place. So now let's focus on using the mean and the standard deviation together to understand how scores are related to other scores in the data set. So I'll start with the coefficient of variation, and then we'll move on to z-scores. So the coefficient of variation is a measure of the standard deviation in terms of the percentage of the mean, or the relative spread. So this is really useful for comparing the consistency between two data sets when their means are very different, because the size of the standard deviation is affected by the scale of the data. So Bob has a lower mean than Maria. So you would expect his standard deviation to also be lower. Given that his standard deviation is higher than Maria's, maybe he's even less consistent than Maria than we thought based on the standard deviation. So that's an example relative to what we've been looking at. Another thing that you can think about, let's say we were looking at two different variables that were measured in very different ways. So let's say we were comparing the standard deviation of age to the standard deviation of number of years in school. And let's say we were looking at a sample of 100 NSC students. Well, if you think about the number of years in school, it's probably going to range anywhere from, 0 to 10 at the very highest. So your standard deviation is going to be somewhere within that range. But if you were looking at age, that can be anywhere from like 17, 18 to 99. I've seen some pretty old people walking around here. So your standard deviation is going to be higher for age, even if age is a more consistent variable than the number of years in college, just because the scale of age has higher numbers in it than the scale for, number of years. So think about that, and that's why coefficient of variation is important, because you control for the difference in scale by controlling for the mean. So how big is the standard deviation relative to the mean of my data set? So look at your calculations. For the population, you take the population standard deviation, divide it by the population mean, multiply by 100. For the sample, you take the sample standard deviation, divide by the sample mean, and then multiply that by 100. So although the mean for Bob and Maria aren't very drastically different, and they were measured pretty much on the same scale, we can use the coefficient of variation to see if the standard deviation actually underestimates how less consistent Bob is compared to Maria, because his mean is lower in general. So we would expect him to actually have a smaller standard deviation because his mean is lower. But he doesn't. It's way higher. So let's use the coefficient of variation to find that out. So you just plug in the sample mean. So for Maria, that's 5.477. Oops. Right there for the sample standard deviation. Plug in her sample mean of 99. And we divide the standard deviation by the mean, so 5.477 divided by 99, and multiply that by 100. So you end up with 0.055 times 100. And her standard deviation takes up 5.5% of the mean. So she's still looking pretty darn consistent. Now for Bob, his standard deviation is 30.583, so that goes here. His mean is 87. Do the math there. He still looks pretty inconsistent, and his standard deviation is 35.2% of the mean. So remember, before I told you that when we calculated the two standard deviations right here, you can see that Bob's is 5.6 times higher than Maria's. Well, after controlling for the overall difference in transaction times, Bob's coefficient of variation is 6.4 times higher than Maria's. So Bob is even less consistent than Maria than what we thought based on the standard deviation. Now let's go ahead and move on to z-scores. So z-scores are a great way to get a standardized score that no matter what distribution you're looking at, the z-score tells you how many standard deviations above or below the mean a particular score is. So it tells you the location of a score in the distribution relative to the mean and how spread out scores are in that distribution. So the z-score has two parts. The first part is the numeric value of what you calculate. That tells you the distance of the score from the mean in terms of standard deviations. So if you have a z-score that's 1, your score is 1 standard deviation away from the mean. Now, the other part of the z-score is the sign. So you can have a score that's above or below the mean. If you have a z-score that's positive, that means that your score is above the mean. So it's to the right of the mean in the distribution. If you have a z-score that's negative, that means that your score is below the mean. If you drew it in the distribution, it's to the left of the mean in the distribution. So think about what the z-score is, and the calculations make sense. So for the population z-score, you are finding the distance between a score and the population mean. So that tells you the raw distance of a score from the mean, but we want to turn that into how many standard deviations does that equal. So we divide it by standard deviation. Same thing on the sample. What's the difference between the score and the sample mean in terms of standard deviations? So remember before I said if you have a score that's plus or minus 2 standard deviations away from the mean, it's extreme. Well, now you can say if a score has a z-score that's greater than the absolute value of 2, it's an extreme score. Now I put absolute value there, those two vertical lines, because we're going to ignore negatives versus positives, just looking at the raw distance from the mean in terms of standard deviations. Because if you have a z-score of -2, it's 2 standard deviations away from the mean. It's just a score that's smaller than the mean, but it's still extreme, just on the low end. If you have a z-value that is greater than or equal to an absolute value of 3, then we call it an outlier. So it's even more extreme than an extreme score. It's something that's extremely odd and that is kind of cause for alarm. Sometimes when people are looking at their data, they'll get rid of outliers completely if they can justify it, which, yeah, there's differing opinions on whether or not that's okay to do. But remember, when you look at the mean, an outlier can completely change your mean, right? It drags it to it. That's why we don't always use the mean when we have skewed distributions. So sometimes it does make sense to get rid of an outlier because it can totally mess up your results. So remember, where we were looking at Maria and Bob, her mean transaction time was 99 and his was 87. and the population mean is 106.733. And if you calculated the population standard deviation, which I didn't have you do, you end up with 24.941. So if the total population mean of all transaction times is 24.971, what would be Maria's z-score? Now I'm treating Maria's mean transaction time as an x value because I'm not comparing one of her transactions to the mean of all of her transactions. I'm comparing the mean of all of her transactions to the mean for everybody in the population. So I'm treating this as an x. So to figure out her z-score, we find the difference between her score, her mean score, and the population mean. So 99 minus 106.733. And then I divide that by the standard deviation for the population, which is 24.941. Now it's important that you put the values in the numerator in the right order, that you put your score before your mean, because if your score is lower than your mean, then you're going to end up with a negative value in the numerator and an overall negative value for z. So we can say that Maria's mean transaction time is 0.31 standard deviations below the mean for the population, and we're not going to call that extreme. So, she's got shorter transaction times than the mean, but she's still lumped in with the majority of people. She's not really that special. She's not extremely short transaction times. Now let's look at Bob. So Bob's score was 87. And the population mean, our mu, is 106.733. Our standard deviation is still 24.941. So z is equal to x minus the mean divided by the standard deviation. So x, 87, minus the mu of 106.733 divided by the standard deviation, 24.941. So 87 minus 106.733 gives you negative 19.733. And then we divide that by 24.941. And you end up with a z-score of negative 0.791. So Bob is below the mean by 0.791 standard deviations. He's also among many other tellers, but he's a bit more extreme than Maria. So his average transaction time is lower relative to the rest of the population than Maria's, which we already knew that. Still not extreme. Now I want to show you guys the empirical rule. So the empirical rule is based on z-scores, and it gives you predictable proportions or percentages of scores in the normal distribution based on the mean and the standard deviation. So here we can see, remember I was telling you that a z-score of 3 or above is extreme, and that a z-score around, or that was an outlier, and then a z-score around, 2 or more standard deviations, between 2 and 3 standard deviations is extreme. So let's take a look at the empirical rule. So the empirical rule just gives you predictable proportions or percentages of where scores fall in your data set in a normal distribution. So it has to be a normal distribution for this to work, and it's based on the mean and the standard deviation. So just to break this down for you, here's our normal distribution. Our mean is smack dab in the middle. 68% of scores in a normal distribution are within 1 standard deviation of the mean. Or in other words, between a z-score of -1 and +1. 95% of scores are within 2 standard deviations of the mean. So -2 standard deviations or +2 standard deviations. So again, 95% of the scores are within 2 standard deviations of the mean in a normal distribution between a z-score of -2 and +2. And then if you think about it, so this represents the middle 95% of the distribution. Well, 5% of that distribution, 5% of the scores are left. So you split that up into both of these ends. So 2.5% of scores have a z-score above 2. 2.5% of scores have a z-score below 2. Now, if you think about the normal distribution, it is symmetrical. So if you folded this in half down the mean, you would see a mirror image on either side. Well, the z-scores also function this way in a normal distribution. So if you think about a z-score of -1, it's the same distance from the mean as a z-score of 1. They're both 1 standard deviation from the mean, just one is above the mean and one is below the mean. So maybe looking at a sample distribution will help you understand not only the empirical rule, but also how z and x values are tied together. So remember, the formula for finding z is z equals x minus mu over sigma, or the score minus the mean divided by the standard deviation. Well, you can reverse engineer this formula to end up with how do you find x based on z standard deviation and the mu. So you can multiply both sides by standard deviation and end up with z times standard deviation equals x minus mu. Then you can add the mu to both sides. You end up with z times standard deviation plus the mu equals x. So that's how I derived that formula based on the mean formula. So what I did was I said, okay, if we had a distribution with a mean of 20 and a standard deviation of 5, for example, I went ahead and filled out all the x values that correspond to all the z-scores that are labeled here. So for example, if I wanted to figure out what is the x value for a z-score of 1 using this formula, well, I could say 1 times the standard deviation of 5 plus the mean of 20 equals 5 plus 20, 25 is the x value. I did that for all the values here. Now, because I have pretty simple mean and standard deviation, you don't have to do all those calculations. Look, you can just say, okay, our starting point is the mean. It's right there in the middle. For a z-score of 1, I add 1 standard deviation. I add 5. For a standard deviation, or a z-score of 2, I just add another standard deviation. I add 5 again. So I'm just counting by 5s. As I go upward to the right of the mean, I'm adding 5 to each subsequent score, represented by 1 more z-score. And then on the other end of the distribution, I'm just subtracting 5. So 15 is 1 standard deviation below the mean, or in other words, 15 is 5 points, standard deviation, below 20, the mean. 10 is 2 standard deviations below the mean, z-score of 2. So 2 5s below 20. Well, 2 5s below 20, 10 below 20 is 10, and so on and so forth. So I hope that that demonstrates how the scores in the data set are tied to the z-scores and how you can figure out what an x value is based on the z-score. And just for example, if we were looking at this, we could say that 2.5% of scores in this data set are above 30. 68% of scores, so the majority of scores, are between 15 and 25. And nearly all scores, 95% of scores, are between 10 and 30. So I showed you the empirical rule, and I showed you an example using the empirical rule to just give you a nice understanding of how z-scores tell you about the location of scores in your data set and how useful it can be when you have a normal distribution. But even if you don't have a normal distribution, z-scores are extremely useful because they tell you where a specific score falls relative to the mean of all scores, while taking into consideration how spread out the scores are in your data set. So sometimes it's way better to make decisions using z-scores than it is to use something like percentiles. So maybe instead of making percentiles the basis for raises and firings, you can use z-scores. So you can think about how extreme scores are without forcing raises or firings. So if you think about it, even if everybody in, for example, Chase Bank on Green Valley Parkway, even if they all perform pretty well, there's going to be some of them that fall above the 70th percentile. There's always going to be, for example, 30% of employees that fall above the 70th percentile, even if all the scores are pretty good and pretty close together. So people are going to get fired even if they're doing well. Then if you think about the more happy side of this, getting a raise, even if everybody is performing poorly, everybody has really long transaction times, there's going to be a certain proportion that fall in the 20th percentile or below. 20% of your population of employees is going to get a raise, even if they are all not doing very well. So that can be really problematic. So a better way to make this decision would be to use z-scores. So let's say we're willing to give somebody a raise if they're, outside of the norm. If we were looking at a normal distribution, which this isn't normally distributed, but just kind of roughly speaking, if they were outside of this range here. So for example, if they were, in this low end of the distribution, outside of the majority. Because remember, this is your frequencies. So, if you have a higher section of your distribution, that means more frequent, right? Most people are here. So it's starting to be, outside of the normal. So in the low end, they would get a raise, lower transaction times. But we're going to be more picky with firing. We don't want to fire anybody unless they have an extremely high transaction time. So a z-score that's greater than 2. So just as a matter of example, I used that mean transaction time for the whole population, the standard deviation, and plugged in each x value here. So this is the population that we're looking at. Now, I encourage you to figure out how I got 24.941 for the standard deviation using this data. Go for it if you'd like. So we're looking at each z-score for each person based on the mean and the standard deviation for the entire population. Well, based on this, there's only going to be 2 raises and nobody's getting fired. And those decisions are far different than what we used when we were looking at the percentile location index at the beginning of this video, where we were forced to fire and give raises to people based on percentiles. Here, this is a little more realistic and a lot more informative because we're looking at, are these people extremely awesome or extremely, well, kind of awesome, right? Not extreme. We're being a little more generous with raises, or extremely terrible. All right. So this was a lot of information. I hope that you are willing to go back and watch portions that didn't make sense. I hope that as you've been going through this lecture, you've been stopping at example problems once I showed you the first one and trying that second version of the example problem before you watch the answers. That's a great way to check your knowledge before you come to class and before you do assignments. And if you have any questions, feel free to ask.